In our last lecture, we have explained the method of point position reduction for function generation and path generation by a Fourier linkage. Of course, the same method is equally applicable for synthesizing slider crank mechanisms. Today, we shall demonstrate the application of this point position reduction towards synthesizing an approximate dual mechanism, which is a 6-link mechanism. So, we would like to synthesize a 6-link approximate dual mechanism and with specified swing angle of the output link. That means, between the extreme position, the output link should swing through a specified amount, and during this continuous rotation of the input link, the output link should have a dual or should not move during some portion of the cycle. Let me explain the principle of this design with the help of the following figure. To explain the approximate dual link mechanism, let us look at this figure. This is the kinematic sketch of a 6-link mechanism consisting of the fixed link, link number 1, link number 2, link number 3, link number 4. This 1, 2, 3, 4, that is O2, A, B, O4 constitutes a 4R planar mechanism. And on this coupler AB, I take a point C, this coupler point. As this crank rocker moves, the coupler point suppose generates this particular coupler curve. As we notice, this portion of the coupler curve from C1 to C2 is can be represented fairly by a straight line, and this will be utilized to design a 6-link dual mechanism. What we do, we put another link 5 at this coupler point C through a revolute pair, and the output link 6 has a prismatic pair between link 5 and this link 6. As we see, this straight line portion of the coupler curve passes through this fixed hinge O6, where link 6 is hinged. During the motion of this crank, as the crank pin A comes from A1 to A2, the coupler point C moves from C1 to C2. Because there is a prismatic pair between link 5 and link 6, during this portion of the movement of the input link, the output link 6 does not move, as the coupler point C goes along this straight line. Beyond that, this output link starts moving in the counterclockwise direction, and the maximum swing angle I can obtain by drawing a tangent to this coupler curve from this O6. So, this angle, let me call theta 6 star, that defines the swing angle of this output link. And during continuous rotation of the crank of this 6-link mechanism, the output link 6 undergoes a dual period when the crank pin A moves from A1 to A2, that is, the coupler point moves from C1 to C2, and it swings through this angle theta 6 star. Let me now explain this with the help of a model. Let us look at this model of this 6-link dual mechanism. These link number 2, 3 and 4, as I said, constitutes a 4R linkage, and this is the coupler point C. And there is a prismatic pair between this link 5 and the output link 6, which is hinged at this point, which we earlier called O6. This is O2, A, B, O4, C and O6. As we give continuous input rotation to this crank rocker linkage, what we should notice that during this portion of rotation of the crank, during this interval of the rotation of the crank, the output link hardly moves, because this coupler point goes along a fairly good approximation for a straight line. And as soon as this comes out of the straight line portion, the output link starts moving, and this is the maximum position, rather the extreme position of the output link, when this line becomes tangent to this coupler curve. Our job is to design these linkages using the method of point position reduction, and we shall use first we shall design a 4-link mechanism with 4 points on this coupler curve, namely C1, C2, C3, C4. Suppose we want to synthesize this coupler curve by allowing the coupler point to pass through these 4 positions, namely C1, C2, C3 and C4. We will design a 4-link mechanism, 4-hour mechanism to generate this coupler curve, only ensuring that the coupler point C passes through these 4 positions C1, C2, C3 and C4. As explained in the last lecture, what we do, we choose O2 and A1 arbitrarily. This is A1, this is O2. Since the link length O2 A1 remains constant, when this link moves, the path of A I can get by drawing a circle with O2 as center and O2 A1 as radius. This is the path of A. I call it KA. Since this link length AC1 is rigid, which does not change as the mechanism moves, corresponding to C2, C3 and C4, I can find the location of the point A and mark them as A2, A3 and A4. So this is the circle which I call KA, that denotes the path of the point A. Now, to locate the location of A corresponding to the second configuration, when C comes to C2, what I do? I measure C1 A1, which does not change. So from C2 I draw this circle and I get the location A2. Similarly, from C3, using the same link length AC, I get A3, and from C4 I get A4. As we know, we cannot choose O4, the other fixed hinge, arbitrarily. We have to choose it such that 4 of the inverted positions of O4 becomes 3 distinct locations. Towards this end, we decide that O421, that is the second configuration inverted on the first configuration, becomes same as O411, which is same as O4. So we choose O4 such that these 2 inverted position coincides. Towards that end, as we know, what we have to do, we take the mid-normal of A1, A2. I draw the perpendicular bisector of A1, A2. This is the perpendicular bisector, and I draw the perpendicular bisector of C1, C2. This is the perpendicular bisector of C1, C2. These 2 straight lines meet at this point, and I choose my O4 at this location, which is same as O411. This will ensure that if second position is inverted on the first position holding the link number 3, that is the coupler fixed, then O421 will also be here. Let me mark these 2 points, namely A2, C2 and O4. Now, if I invert it on the first position, that A1 and C1, A2 goes to A1 and C2 goes to C1, as we see that the O4 does not move and gives me the location of O4 to 1. Next, to get the inverted position corresponding to third and fourth configuration, we go as usual A3, C3, O4. Then A3 coincides with A1, C3 coincides with C1, and wherever O4 goes, that I call O431. So I can pierce my tracing paper and mark that point on the drawing sheet, which is O431. Then for the fourth position, we follow the same technique. We mark A4, C4, O4. Move the tracing paper such that A4 coincides with A1, C4 coincides with C1, and wherever O4 goes, that I mark as on the tracing paper as O4, 4, 1. Since the coupler was held fixed, that means the point B on the coupler was not moving, and O4B is a fixed length, O4 moves on a circle, and the center of the circle passing through these 3 points will give me the location of B1. So we have got the 3 inverted positions of O4 as O4, which is same as O4, 1, 1, and also O4, 2, 1. So 3 distinct locations for the 4 inverted positions of O4 here, then O4, 3, 1 is here, and O4, 4, 1 is here. So the center of the circle passing through these 3 distinct locations I can find out by drawing the perpendicular bisector of this line and perpendicular bisector of this line. These 2 perpendicular bisectors intersect here, which gives me the location of the other coupler hinge B1. So at this stage we have reached up to the design of the 4-bar linkage, namely O2 A1 O4 B1 A1 B1, and ABC is the coupler at the first configuration, that is C is the coupler point C1, so we have reached the first phase of the design, namely O2 A1 B1 O4, and A1 B1 C1 is the coupler. At this point C1, we put the, with a revolute pair, we put the 5th link, link number 5. And as we noted that if this is the straight line portion of the approximate straight line portion of the coupler curve, then O6 must be located on the extension of this line. O6 will lie here. Now if we specify the swing angle of the output link 6, say equal to 30 degree, then O6 must be so located in this line that the tangent drawn from O6 to this coupler curve will be at 30 degree to this line. So what you can do, we can draw a line which is at 30 degree this line is at 30 degree to this line, the approximate straight portion of the coupler curve. Then I draw a tangent to this coupler curve parallel to this line This line is tangent to this coupler curve, which is generated by this 4R link, namely O2AB, O4, and this line is parallel to this line, which was at an angle 30 degree to this line. So location of O6 should be here. So I put a revolute pair at O6. Then the swing angle of the follower link, that is link number 6, which has a prismatic pair with link number 5, this angle is 30 degree, which we call theta 6 star. So let me go through this process all over again. We wanted to generate this particular coupler curve, and we took 4 points on it, C1, C2, C3, C4. C1, C2, C3 to ensure that there is an approximate straight line portion. Then we choose O2 and A1 arbitrarily, choose O4 such that two of the inverted positions of O4, namely O4, 2, 1 and O4, 1, 1 coincide. To do that, we drew the perpendicular bisector of A1, A2 and C1, C2, and wherever these two lines meet, that locates the point O4, which is same as O4, 1, 1 and O4, 2, 1. Then using the tracing paper, we obtain the inverted positions O4, 3, 1 and O4, 4, 1. The center of the circle passing through these 3 points was located at B1. So that located the B1 and the coupler length AB. We can also verify that this O2, AB, O4 is a crank rocker such that this link A2, A1, the shortest link, can rotate completely. Then we knew that the other fixed hinge O6 connected to the output link 6 must be on this line, which represents approximately the straight line portion of this coupler curve. I have joined C1 and C2 and extended that line. Now the location of O6 on this line should be such that the swing angle of the rocker is specified as 30 degree. So I drew a line which is at 30 degree to this line, and then drew a line parallel to this line but tangent to this coupler curve. So that located the point O6. I drew a tangent parallel to this coupler curve but at an angle 30 degree to this line C1, C2. So that completes the design of this 6-link mechanism. So we have just now seen how we can synthesize a 6-link approximate dual mechanism with specified swing angle of the output link. We use the 4-position coupler curve generation with the point position reduction technique. We took C1, C2, C3, C4 suitably to give the desired coupler curve. Then we chose O2 and A1 arbitrarily and applied the point position reduction technique, and O4 is so chosen that O4, 1, 1 and O4, 2, 1 coincide. Then we completed the design first of the 4-link mechanism. Then we chose the fixed hinge O6 suitably to give the specified swing angle of the output link. We of course have to check the Grasshopp's criterion for the design linkage O2, AB, O4 to ensure that we have really got a crank rocker. Next we discuss what we call dead center problems. That is, we have to design linkages for given extreme configurations of the output link. We can do it for the slider crank mechanism with slider as the output link, and also for 4R crank rocker mechanism where obviously rocker is the output link. First let us discuss the slider crank synthesis for specified dead center configurations. For this, we are given the desired stroke length, which we call SH, and the crank rotation as the slider moves from the outer dead center to the inner dead center configuration. Let me explain this with the help of a figure. This figure shows a slider crank mechanism 1, 2, 3, 4 in two of its extreme positions. Here, as you note, the crank O2A1 and the connecting rod A1B1 have become collinear in the same direction, giving one extreme position of the slider, which we call the outer dead center. Again, as the crank rotates and this crank pin A1 comes to A2, again the crank O2A2 and the connecting rod A2B2 have become collinear, giving rise to the other extreme positions, which we call the inner dead center. At the outer dead center, the slider is farthest from the crankshaft, and for the inner dead center, the slider is nearest to the crankshaft. So, as the slider moves through B1 to B2, that is, the stroke length is given by SH. So, SH is specified, and the rotation of the crank as it moves from outer to inner dead center, that is the rotation from O2A1 to O2A2, given by this angle theta 2 star. So, what is given to us is the stroke length SH and theta 2 star, and we have to come up with the required dimensions of the slider crank, namely the crank length L2, the connecting rod length L3, and the offset, that is the distance between the crankshaft and the line of movement of the slider, as E. So, there are three kinematic dimensions, namely O2A1, A1B1 and E. Given to us is SH and theta 2 star. As we see, from B2 to B1, the return movement of the slider, during this return movement of the slider, the crank rotates from O2A2 to O2A1 through an angle which is less than pi, and through the movement from B1 to B2, the movement is through theta 2 star, which is more than pi, and this angle is the difference between theta 2 star and pi, that is the angle between O2B1 and O2B2, this angle. So, theta 2 star bar, this angle is theta 2 star minus pi. So, we can derive also the quick return ratio for this slider crank mechanism. Quick return ratio is, during, assuming of course that the crank is rotating at uniform crank speed, uniform angular speed, then the forward motion is theta 2 star, which is pi plus theta 2 star with a bar, and this angle is pi minus theta 2 star bar. So, if the quick return ratio, desired quick return ratio is given, then also we can obtain theta 2 star bar, and from there I can obtain theta 2 star. To solve this problem geometrically, what we should notice that for a given quick return ratio, this angle is fixed, theta 2 star bar, which you can solve from this equation, and this is the stroke length SH. As a result, the point O2 must lie on a circle passing through B1, B2 and O2, since the circumferential angle of a circle remains constant. O2 can be anywhere on this circle. If I draw a circle through B1, B2 and O2, this is the circle which passes through B1, B2 and O2. Now, if O2 is here on this circle, because it is the same chord length B1, B2, the circumferential angle at O2 will remain same. Thus, we see O2 can be chosen anywhere, which will immediately change all the dimensions L2, L3 and E. So, there is no unique solution. In fact, there are infinite solutions. So, we have to choose one of the parameters out of L2, L3 and E. Out of these three kinematic dimensions, we have to choose one, and determine the other two to get a unique design. If all these parameters are left unknown, then there can be infinite solutions. So, first we show that geometrically how can you obtain L2 and L3 if we assume a given value for this E. We have been given the stroke length B1, B2 as SH. So, I draw a line B1, B2 along the line of movement of the slider of length SH. Now, we have seen O2, that is the crankshaft, should be so located that this B1, B2 subtends an angle theta 2 star bar at O2. Theta 2 star bar we can obtain from the desired quick return ratio. So, our objective is to draw a circle passing through B1, B2 and O2 such that at O2 we get an angle, circumferential angle, that is this angle B2 O2 this angle should be theta 2 star bar. We can do that very easily geometrically by drawing the mid normal of B1, B2. This is the perpendicular bisector. So, the center of the circle must be on this line, and if this is the circumferential angle, then the central angle must be twice of that, twice theta 2 star. So, what I do at B1, I draw a vertical line, draw a line at an angle theta 2 star bar in the clockwise direction, and where this line intersects the perpendicular bisector, that gives me the center of the circle as CO2. So, now with this point as center and CO2 B1 as radius, I draw this circle, which obviously passes through B2 and also subtend an angle any point on this circular arc, the same angle theta 2 star bar. Because we have assumed the kinematic dimension, the offset E. So, I draw this line at a distance E from B1, B2, and wherever this line intersects the circle, that locates my crankshaft O2. Once I have obtained the crankshaft O2, I can easily find the connecting rod and the crank length, because O2 B1 at the outer dead center is nothing but L3 plus L2, where L3 is the connecting rod length and L2 is the crank length. Similarly, O2 B2 at the inner dead center configuration, O2 B2 is L3 minus L2. So, out of the three kinematic dimensions, to define the linkage, I assume E and determine L3 and L2 from the measurement of O2 B1 and O2 B2, and then solving these two equations. However, if L2 or L3 is given, then it is much easier to solve the problem analytically rather than graphically. Of course, it can be done graphically, but the graphical construction will be much more cumbersome. So, let me do that analytically, assuming that one of these two lengths L2 or L3 is given, and find the other two dimensions, namely E and L3 or E on L2. If one of the link lengths L2 or L3 prescribed, then let us go back to this figure showing the outer dead center configuration and inner dead center configuration. SH is given to us, theta 2 star bar is given to us, and one of the link lengths, say L2 or L3, is given to us. So, what we do, we see this triangle O2 B1 B2, O2 B1 B2. In this triangle, if I apply the cosine law, I can write SH squared is L3 plus L2 whole squared, that is O2 B1 squared, plus O2 B2 squared, that is L3 minus L2 whole squared, minus twice of O2 B1 into O2 B2, that gives me L3 plus L2 into L3 minus L2, that is L3 squared minus L2 squared into cosine of this angle, that is theta 2 star bar. Applying the simple cosine law for the triangle O2, B1, B2, I get this equation. If we simplify, we get 2L3 squared into 1 minus cosine theta 2 star bar plus 2L2 squared into 1 plus cosine theta 2 star bar. In this equation, SH is given to us, theta 2 star is given to us from the quick return ratio, and one of these, either L2 or L3 is given, so I can solve for the other. So once we have solved for, suppose L2 is given, then I can easily solve for L3. And once we have solved for L3, I can easily find this offset or E. For that, I draw this perpendicular from O2 to the line of B1, B2, which is the offset E. Again, I apply the sine law in this triangle to determine this angle. Let me call it psi. So what we get? SH divided by sine of theta 2 star bar, SH divided by sine of the opposite angle is O2 B2 by sine psi. O2 B2 is nothing but L3 minus L2 divided by sine psi. With L2 given, I have already solved for L3, so I know this side. So this is given to us, this is given to us, so I can easily find sine psi. And this E is nothing but O2 B1 sine psi, which is L3 plus L2 sine psi. I can easily substitute for sine psi from here, and we get L3 squared minus L2 squared into sine theta 2 star bar divided by SH. So given stroke length, given quick return ratio, given L2, first we solve for L3 and then I can find E. Or the other way around, if L2 is given, L3 is given, then I can find L2 and then again I can find E. So this completes the dead center configuration problems for designing or synthesizing a slider crank mechanism of given stroke length and given quick return ratio. We have just now seen how we can do either geometrically or analytically synthesis of a slider crank mechanism for given extreme configurations where the stroke length SH is given and the quick return ratio is given, assuming of course that the crank is rotating at uniform speed. The problem was to determine the three kinematic dimensions: crank length L2, connecting rod length L3 and the offset E. We have also seen that infinitely many solutions are possible if we leave all these three as unknowns. Then we showed that we can either determine L2 and L3 assuming E, or assuming L2 we can determine L3 and E, or assuming L3 we can determine L2 and E. Because there are infinitely many solutions possible, the best design will be that which makes the minimum transmission angle maximum. This we can do only by trial and error. So we assume one kinematic dimension E or L or L3 to get a unique design. Because infinitely many solutions are possible when all of these are variable, then I can go for the best design mu min max by trial and error. Next we shall discuss the dead center problems for 4R linkages, that is the crank rocker mechanisms for given swing angle theta 4 star and the crank rotation theta 2 star as the rocker moves from outer to inner dead center configuration. We shall now discuss the synthesis of 4R crank rocker mechanisms for given dead center configurations. We shall follow the method what is known as Earle's construction. Unfortunately, the theory behind this Earle's construction cannot be explained in this course, but we shall still discuss the method because it is a very useful technique for designing a useful mechanism, that is a 4R crank rocker with rocker swing angle theta 4 star prescribed and the crank rotation theta 2 star also prescribed as the rocker moves from outer to inner dead center configuration. Here, as you will see, the quick return ratio will be defined as theta 2 star by 2 pi minus theta 2 star. We shall discuss the cases separately for theta 2 star more than pi, theta 2 star less than pi, and if theta 2 star is pi plus theta 4 star. As we shall see from the geometrical method, there will be infinitely many solutions and we can choose the best design to maximize the minimum transmission angle, that is to design for mu min max. We shall explain all these graphical methods to the help of figures. Let me now explain this Earle's construction for the design of a 4R crank rocker mechanism where the swing angle of the rocker is prescribed theta 4 star as the rocker moves from the outer dead center to inner dead center. The corresponding rotation of the crank is through theta 2 star in the counterclockwise direction. We are considering the case where this theta 2 star is more than pi. Theta 2 star is more than pi. We choose O2 and O4, the location of the two fixed hinges, conveniently on the frame. Then I draw a line at O2, this line, at an angle minus theta 2 star by 2 with O2 O4. This is minus because this is clockwise, whereas theta 2 star is counterclockwise. Because this is more than pi, this angle is drawn at an angle which is more than 90 degree. At O4, I draw this line which is at an angle minus theta 4 star by 2. Minus is clockwise because theta 4 star is counterclockwise. And these two lines drawn at O2 and O4 meet at this point R. Then we draw a circle with O2R as the diameter. This circle I call KA1. The circle with O2R as diameter. Next, we draw the perpendicular bisector of O2R, that is this line. This line is 90 degree to O2R and passing through the midpoint of O2R. This line meets O4R at the point CB1. Then I draw a circle with CB1 as center and CB1R as radius. This is this circle. Obviously, that also passes through O2, and this circle I call KB1. Next, I draw a line at O4 at an angle minus theta 4 star. This is clockwise, so I call it minus theta 4 star. This line is O4N intersecting KB1 at N, and KB1 intersects the line O2, O4 when extended at this point S. Then B1 can be chosen anywhere on this circular arc from N to S on KB1, but not on this side, to the right of N and above S. B1 I can choose anywhere on this circular arc. And if I join O2 with B1, that line intersects the previous circle KA1 at the point A1. Then O2, A1, B1, O4 gives me the desired 4R crank rocker linkage at its outer configuration. This is what we know as Earle's construction, but as I said, the proof of this construction is beyond the scope of this course. Let me now demonstrate what happens if theta 2 star is less than pi. That we will see in the next figure. Let us look at this figure of Earle's construction where theta 2 star is less than pi. Rest of the specification as before. Theta 4 star is the swing angle of the rocker from outer to inner dead center in the counterclockwise direction. Corresponding rotation of the crank is through theta 2 star in the counterclockwise direction. Previously we had theta 2 star more than pi, and now we have theta 2 star less than pi. Just as before, we choose O2 and O4 arbitrarily. We draw the same two lines at O2 at an angle minus theta 2 star by 2 with O2 O4, and at O4 at an angle minus theta 4 star by 2, this line with the same O2 O4 extended. These two lines meet at R as before, and I draw KA1 with O2R as the diameter. Up to this point there is no change. Then I draw the perpendicular bisector of O2R, and this line, the perpendicular bisector, meets O4R at CB1. With CB1 as the center and CB1R as the radius, I draw this circle which I call KB1. Again, up to this point there is no change whether theta 2 star is more than pi or less than pi. The construction of KA1 and KB1 remain as before. But now as we see, if I draw the line O4N at an angle minus theta 4 star, then that line O4N comes out like this, intersecting KB1 here again at S. Previously this point of intersection was below O2 O4, and S I considered the intersection of KB1 with O2 O4. Here N and S are both points of intersection of this line O4N with KB1. Then the point B1 can be taken anywhere on this KB1 on this circular arc NS. It cannot be here, it cannot be below S. It has to be taken within this range NS of the circular arc belonging to the circle KB1. I have taken B1 here, and I get a design by joining O2 B1 which intersects KA1 at A1, and O2 A1 B1 O4 gives me the desired 4R crank rocker linkage satisfying the desired extreme positions of swing angle theta 4 star and the corresponding crank rotation theta 2 star. As we see, because I could have taken B1 anywhere, I get infinite number of solutions, and the same is true even for theta 2 star more than pi. So this particular design I can parameterize by this angle beta. I can see beta can take any value from if I join O2S and O2N. So there are infinitely many solutions for various values of beta, and that is true for whether theta 2 star is more than pi or less than pi does not matter. It always gives me infinite number of solutions. The best solution for beta can be read from a nomogram which we are not showing here, known as Folmer's nomogram, and we know the optimum value of beta which will make the minimum transmission angle maximum. That means mu mean will be maximum for a particular value of beta, and that value of beta can be read from a nomogram known as Folmer's nomogram. At this stage, I would like to point out what happens if theta 2 star is more than pi, but theta 2 star is say pi plus theta 4 star. To explain this, let me go back to the previous drawing. Looking at this figure which was drawn for theta 2 star more than pi, let us consider the special case if theta 2 star happens to be equal to pi plus theta 4 star. That means theta 2 star by 2 is pi by 2 plus theta 4 star by 2. Now look at this construction. This angle is theta 2 star by 2, this angle is theta 4 star by 2, which means this angle is also theta 4 star by 2. If this is pi by 2 plus this, then this angle will be 90 degree. So this line will be perpendicular to O2R. As a result, this perpendicular bisector and O4R will never intersect, because this angle is also 90 degree, this angle is 90 degree, and these two lines become parallel and they will never meet. Consequently, the center CB1 goes to infinity, and this KB1 with CB1 as center degenerates into a straight line passing through O2 and R. That means KB1 will be the straight line which is nothing but extension of O2 R. So, if I draw this O4 N, this line at an angle theta 4 star, they will intersect at some point. And N, this is the circle of infinite radius KB1. This is KB1 when CB1 goes to infinity, because theta 2 star by 2 is pi by 2 plus theta 4 star by 2. So, N is the intersection of these two lines. Then B1 can be taken anywhere on this line, but beyond this point N. That will, B1 will be anywhere on this line beyond this point N, say here, and B1 I can choose there, and O2A1 will be always equal to O2R. That means we get a design, infinite number of designs, but every time the crank length remains the same as O2R, because KA1 is this circle which has not changed. So, under this situation L2 does not change, and this CB1 goes to infinity. That means this KB1 degenerates into a straight line, and B1 can be taken anywhere above this point N on this line. So, that is a very special case. Let me now summarize what we have discussed today. Besides discussing the design of an approximate dual mechanism having 6 links starting from a coupler curve, we have also discussed the dead center problems, that is designed for extreme configurations. The outer and inner dead center are the two extreme configurations, and we have discussed both slider crank and 4R crank rocker mechanisms. For the 4R crank rocker mechanisms, we considered 3 cases separately, where the theta 2 star, that is the crank rotation, as the rocker moves from outer to inner dead center by an angle more than pi, less than pi, and a special case if theta 2 star is pi plus theta 4 star. In all these cases, what we have seen that the Earl's construction gives us infinitely many solutions. The optimum solutions is that for which the minimum transmission angle mu mean is maximized, and that design means which is parameterized by the angle beta in all our figures can be obtained by using a nomogram which is known as Folmer's nomogram, which we have not discussed in this course. This brings us to the end of the graphical method of kinematic synthesis of planar linkages. In our next lecture, we shall start the discussion on analytical method of kinematic synthesis of planar linkages.